Hello everyone. Experiment 1 is Uniaxial tensile test. So the objective of this test is to find out the maximum tensile stress and the Young's modulus by constructing true stress versus true strain curve. The equipments and tools required for these experiments are UTM machine, the tensile grips, vernier caliper and extensometer, marker, and the most important, the specimens. We will perform the experiment on two different material. One is aluminum, second is mild steel. I will give the brief of the machine first. This is the UTM. We call this as a universal testing machine. It is of make Lloyd instruments and the load cell capacity is 100 kilonewton. So this can take or test a specimen up to the 100 kilonewton. This is the crosshead, which is moving part. These two studs are given. One stud is fixed and this one is movable. So we will mount our grips in the two studs. So let's see the mounting of the grips. First I will mount the bottom grip. You just need to press inside the stud and lock it by using the pin. Then the upper grip, you hold this pin in your hand, push inside the stud and lock it. These are the spacers given by the company to restrict its movement. So yes, our grips are mounted. Now we can mount our specimen in between these two grips. These grips are mechanical grips. You can see we can mount the specimen or hold the specimen by moving this wedge action jaws. So let's first mount the top portion in the grip. Let's take this machine up. Yeah. So here we have mounted the upper portion in the upper jaw. To mount the lower portion in the lower jaw, we need to move this crosshead down. So I am using this console or a kind of remote control to take this crosshead down. Yes, so your specimen is mounted in the grips. So this is the extensometer we are talking about. We have already marked the lines over here, the center line to the specimen, and the two lines, it is 10 mm apart because the gauge length of this extensometer is 20 mm. And it is having a pointer and the dial which is having the displacement up to 50 microns. This gives the readings in the microns. So to the safer side, I won't go the reading up to the 50 microns. We will stop or we will take this out from the specimen once it reaches to 40 microns. So let's see the mounting of the extensometer on the specimen. Yes, so extensometer is mounted on the specimen and this needle I have set it to the 0 position. Let me tell you how I am taking the readings. So already I will make a table of displacement like 2 micron, 4 micron, 6 micron up to the 40 microns. That will be my one list, and on this console you can see like it will give the load values over here on the display. So when this needle goes to 2 micron, the corresponding load value I will note it down manually. It has no connection with the software. These readings we have to note it down manually. So let's start the test. So now we can edit the parameters for this test now. Here you can see that it is already showing the compression. This direction of loading I can change to tension, and the speed is 1 mm per minute, and limit also I can change. So here I don't give any limit to this machine. Once this specimen get break, it automatically gets stopped. So as usual, before starting we need to tear out the values of load and extension. So yes, I am tearing this off. So we are doing a test on aluminum at speed of 1 mm per minute. So let's start, and simultaneously we also have mounted the extensometer on the specimen, that readings also be noted by me. So I am starting the test now. Yes, it is started. So let's move on to the extensometer to see its movement. You can see the pointer, it is aligned to 0 now. So as this load increases, the pointer will start moving. The pointer is reaches to 20 microns. Once it reaches to 40 microns, I will take out the extensometer out, and the machine will keeps on operating till failure. Yes, so I am taking this out now. Yes, so you can see the aluminum specimen is broke or tested. So I will remove this specimen out and we will mount the mild steel specimen in the grips. We have mounted the mild steel specimen in the same manner how we have done for aluminum. So extensometer is again mounted on this thing because we need the two separate datas. One is from extensometer and other is from machine also. So let's start the machine by using the software. Again we need to tear off the load and extension values now before starting. So yes, it is teared and we need to edit the parameters. Let's see, the direction is tension, the extension rate is 1 mm per minute, and there should be no limit because we are saying that the machine should stop after the specimen broke. So I am starting the test now. Yes, it is started. So here you can see the extensometer displacement is 10 microns and the corresponding load value is 3674 Newton. So like this we need to take the readings for extensometer and the load value. Extensometer is 30 microns, load value is 11,215 Newton. Once that needle reaches to 40 microns, I will take that extensometer out. Yes. The mild steel specimen is also broken, and the tensile test experiment conducted on both the materials, aluminum as well as mild steel. So this is the broken specimen for aluminum. You can see the broken region, the diameter got reduced, and this we call as a cup and cone failure. So this reduced diameter we will post it to you for calculating the percentage reduction in cross section. In the same manner, you can see the failure of mild steel also. Both the cross sections we will send you in the data points, the diameter of initial diameter and the final diameter after breaking. So for your lab purpose, I think this tensile test is conducted well on two materials. Thank you.